the West Coast, obviously. So, and he'll tell us about topological phases of matter.
Okay. Okay, can you see my screen? Everybody can see my screen? Yeah.
Yes,
okay,
we can see it's a little bit small.
It's small.
No, it's perfect.
It's good. Okay.
Hi.
Okay, great. Thanks for the invitation. Sorry, I got the time zones mixed up. So this is going to be sort of mostly a review talk. I'm just going to, say some things about strongly correlated phases of matter, and how a condensed matter theorist thinks about these things. So I realize that the audience is a little more mathematical than the usual audience I speak to. So roughly speaking, the sort of main thrust of this talk, the main idea is that while for free fermion systems, there's sort of a wealth of techniques and sort of really a rigorous framework for understanding them. For strongly correlated phases of matter, which I'll sort of define in a slightly more precise sense, there really isn't such a rigorously developed framework. Instead, what we have is really kind of a patchwork of various ideas and intuitions, some of which are formalized, some of which aren't, which kind of together fit into this kind of coherent whole and allow us to make progress in understanding these strongly correlated phases. So I just want to kind of, for this audience, I kind of want to describe some of these kinds of ideas that appear. Okay, so right, so I figure it's always good to start a talk with a picture. Just before I lose everybody with some dry formalism, it's good to have some pictures. So just so we're sort of all on the same page, here is a bunch of examples of phases of matter, quantum phases of matter that a typical condensed matter theorist or experimentalist would study. And so, I just want to make a couple of points about these pictures. So all these pictures that you see, the sort of various behaviors that are illustrated here, these are all, all these behaviors are driven by the sort of quantum behavior of electrons, many electrons sitting in the background of a periodic lattice of the ions. So, obviously condensed matter is very complicated. There are, there are a lot of various effects going on, but the sort of beautiful thing is that really most of the physical behavior here can be modeled by electrons moving in some periodic background potential and interacting with each other. So that's sort of one important point that I want to make. Another point is that while typically one kind of thinks about the top two examples that I gave here, that of a metal and insulator, as really being sort of examples of free fermions. So metal and a band insulator can be understood from a free fermion perspective. And traditionally, the bottom two examples, the ferromagnet and the superconductor, are sort of understood as being driven by interactions between the electrons, or maybe mediated by phonons. Really, from sort of the standpoint of thinking about exotic strongly correlated phases, all these phases are kind of boring. The point is that even though sort of interactions are involved in realizing these phases in nature and in the physical world, they can all be understood. Even the bottom two phases can be understood from some effectively free fermion mean field perspective. So, this is kind of actually a general point. which is that, like 90%, maybe even more, of the phases that, condensed matter experimentalists work with are sort of boring from the point of view of, somebody who's interested in really exotic, strongly correlated phases, like this community. Well, okay, I shouldn't assume too much about this community. People like me. So that's just so that we're all on the same page. So now let me sort of just build up again build up some formalism. So as theorists, we like to have some well-defined framework for studying things, and we kind of like to abstract out sort of all the details and kind of crystallize it into some well-defined framework. So all the phenomena that I described on the previous slide can in principle be captured by something called the tight binding model, lattice tight binding model. And this is sort of the workhorse of condensed matter theory. This is somehow the setting in which we realize all these phases. And so so the idea is that you model your system by, you have a lattice and you take a many-body Hilbert space or a Fock space to be a Z2 graded tensor product of fermionic Fock spaces, of local fermionic Fock spaces. Okay, so this is kind of the picture that you have in the back of your head for studying all these strongly correlated phases. There's a lattice. There are site Hilbert spaces, which in the simplest case are just fermionic Fock, two-dimensional fermionic Fock spaces with the usual anti-commutator algebra, and all the action happens in this Z2 graded tensor product of these fermionic Fock spaces. So this is the many-body, exponentially large many-body Hilbert space. And here's a sample Hamiltonian that includes both free fermion terms as well as interactions. Okay, so just to sort of reiterate the point that I made earlier, one can realize quite a large number of phases with just free fermion Hamiltonians. Just these kinds of quadratic Hamiltonians, which are in some sense easy to solve because they just require diagonalizing a matrix which is polynomial in system size. Those kinds of Hamiltonians can in principle realize a lot of different phases, including a lot of phases that are pretty popular, like topological insulators, interquantum Hall effect, standard symmetry breaking phases. And so that's not to say that interactions are not important for realizing those phases in nature. You do need interactions for realizing some of these phases in nature. That's just to say that within for the given phase within the phase diagram, for these phases on the left, there's always some Hamiltonian, some free fermion Hamiltonian, which sort of realizes the universal property of that phase. So interactions, as far as sort of the kinds of phases that actually require strong interactions, these exotic, strongly correlated phases that I'll spend the rest of the talk discussing, as far as those, there aren't actually a lot of them, but people do spend a lot of time thinking about them. So the sort of most important ones are these fractional quantum Hall effects, which were discovered in the 1980s, and they're not even really sort of phases of electrons and materials. They're sort of engineered quantum well structures. And then there's an example of a phase of spins in sort of quasi one-dimensional materials, which also realizes something called the symmetry protected topological phase, which I'll mention later. And of course, there are sort of many models, theoretical models that support so-called anionic stations, which some of which are sort of conjecturally realized in so-called spin liquid materials, but that's sort of at a more conjectural level. So again, sort of the upshot is that many of the phases that condensed matter experimentalist theorists deal with are actually sort of on the boring side. There are really very few experimental realizations that really require these strong interactions, but they're somehow, from many of our standpoints, the really the interesting ones. So in the rest of the talk, I want to I want to sort of emphasize that again, while for these free fermion phases, there's really a wealth of techniques and sort of a rigorous framework for understanding them. On the strongly correlated side, like I said, there's sort of really just a patchwork of ideas and various techniques, which don't necessarily all have a rigorous basis. They all rest on some sets of assumptions, but nevertheless, there is kind of really a beautiful structure that does emerge if you sort of coherent structure that does emerge if you put these things together. So I want to for the rest of the talk describe some of these techniques. And in particular, I want to focus on quantum information theoretic tools. So quantum information theoretic tools are sort of a relatively recent addition to this toolbox for understanding strongly correlated phases, but nevertheless, I think they're sort of an important one, and they somehow are a nice sort of complementary set of tools to the usual techniques. Okay. So before I sort of discuss these various ideas that physicists use to understand these phases, let me just make one sort of simplifying assumption. We started off talking about systems of fermions. There was a Z2 graded tensor product involved. There was a fermionic Fock space. Just for simplicity, I want to now restrict to talking about bosons. So you can think about a bosonic Hilbert space as being just an ordinary tensor product of local sort of so-called spin Hilbert spaces. And okay, the physical world is made out of fermions, but a lot of the times you can sort of model a bosonic Hilbert space effectively as sitting inside a fermionic Fock space. Okay, so for instance, this is the way that quantum magnets arise. Quantum magnets, I mean, they are fermionic systems. But the spin of the electron, if a site is occupied by a fixed number of electrons, let's say 1 electron, then the spin of that electron becomes effectively a bosonic variable. Okay, so this is, of course, one can extend results to the case of sort of to the general case of fermionic Fock space, as I mentioned earlier. But it turns out that it's sort of just convenient to develop a lot of the formalism, a lot of the ideas for bosonic Hilbert spaces. Okay, so this is an example of a bosonic Hilbert space. Again, the point is that now operators on separated sites commute as opposed to anti-commuting. Here's an example of a Hamiltonian so-called Heisenberg model. Okay, so let me start by describing some of this patchwork of intuitions that allows us to understand strongly correlated systems. And again, I want to just re-emphasize that this is not a rigorous framework. This is a patchwork of intuitions, which is nevertheless fairly powerful, but it's a patchwork of intuitions. I don't know why this line is sideways. This should be a vertical arrow that indicates. So what you're looking at here is the spectrum of a Hamiltonian, the spectrum of the many-body Hamiltonian. Again, I want to emphasize this is the many-body Hamiltonian in this sort of exponentially large Hilbert space. So the first property that's sort of somehow extremely important in classifying phases is this property of a many-body gap. Of course, one can also talk about phases which are gapless, and there are techniques for dealing with those, but they're not as well developed as techniques for dealing with gapped phases. Okay, so a gapped phase is one where there's either a single ground state or depending on topology, there can be some discrete set of ground states, but then there is a gap, which here I've denoted by delta, from that ground state to the spectrum of excited states, which is sort of remains in the limit of thermodynamic limit of infinite system size. I mean, obviously, for any finite system, there's a gap. I mean, there's generically a discrete spectrum. Sorry, was there a question? No. There's generically this discrete spectrum, and there's a gap. But the point is that we're really dealing with the thermodynamic limit of infinite system size, and we want to have a gap in the thermodynamic limit of system size, infinite system size. Again, I will not formally define sort of the thermodynamic limit of infinite system size, but and then that is a thing that's sort of difficult to formalize. But again, the intuition is that the finite gap remains as the system size is taken to infinity. Okay, So, the nice thing about having a system with a gap is that there's a corresponding intuition that, when there's a gap in a given quantum mechanical system, then, somehow at low temperatures, at temperatures which are much smaller than the gap, the physics of the system is really just the physics of the ground state, right? If you sort of think about the Boltzmann ensemble, at very low temperatures, it's mostly just this ground state. You're just sitting in this ground state. So the various physical properties at low temperature are really properties of the ground state. So that's number one. And number two, to understand this ground state, to understand the various properties of this ground state, we can sort of look at the spectrum of sort of lowest energy excitations above this ground state. And the intuition that is that when there's a gap, excitations above this ground state can be sort of localized within a certain correlation length. Okay, so the intuition sort of coming from field theory is that when there's a gap in this many-body spectrum, there's a corresponding correlation length that scales inversely with the gap. Basically says that correlation functions decay exponentially with this correlation length, with this characteristic correlation length. And for our purposes, what it means is that we can have sort of well-defined local excitation. So this is sort of my attempt to define a local excitation. So let me actually, try to say a little bit more precisely what I mean by a localized excitation, because it's an important concept. But very roughly speaking, a localized excitation, which I've denoted by this sort of orange blob. This is sort of the best that Keynote would let me do. A localized excitation above the ground state, okay, here I have two of them, is some state, which I've called psi, which might be kind of a mess within this region near the excitation, but far away from the excitation, sort of several correlation lengths away from the excitation, like out here, for instance, the state looks exactly like the ground state. So this can be sort of formalized, again, not completely formalized because there's approximations here, but this can be sort of formalized as just saying that if you look at this many-body ground state of the state with the excitations and you trace out everything except for some region far away from the excitations, it looks like the ground state. Okay, so that's what this equation is saying. So this is sort of a way of formalizing the concept of a local excitation. Now, many of the models that theorists play with for realizing these exotic phases of these exotic strongly correlated phases are exactly solvable. They're so-called, there's a class of so-called commuting projector exactly solvable models. And in those cases, this equality is exactly and sort of very easy to check that this property is true. And so in those cases, one can really precisely make sense of this notion of localized excitation. But in general, we sort of expect this to be true, for a general strongly correlated system with a gap. Excitations in a strongly correlated system with a gap. Okay, so this sort of gives us the notion of a localized excitation. So using this notion of localized excitation, we can define the notion of anyons or topological excitations. So, localized excitations I already defined are sort of ones that look like the ground state far away from the excitation, sort of topologically trivial patches away from the excitation, whereas local excitations, so truly local excitations, are ones which can be formed from the ground state by acting with a unitary operator that acts sort of just within the region of the excitation. So they're ones that can be sort of popped out of the vacuum by acting just on the ground state with this kind of unitary operator. And so then the idea is that there is a sort of characteristic spectrum associated to any gapped Hamiltonian of so-called anyon excitations, which are localized excitations modulo local excitations in a rough sense. Okay, so for all the sort of like for all the free fermion phases, all the sort of boring phases I mentioned, the spectrum of anyons is trivial. So every localized excitation can be made locally. But for a so-called topologically ordered system, a system with intrinsic topological order, such a system is sort of precisely characterized by the fact that it has a non-trivial spectrum of anyon excitations. There are localized excitations which nevertheless cannot be made locally. They carry some of this so-called topological charge. So, if you've seen the toric code, things like this, those are sort of prototypical examples of systems with intrinsic topological order.
Don't anyons only exist in 1+1 dimension?
Anyons exist in do not exist in systems in one spatial dimension. They exist in 2 and higher spatial dimensions.
Okay, but only on lines, or?
No, the anyons can exist sort of anywhere in, like, if you're in 2 dimensions, they can exist anywhere in 2-dimensional space. But when you're trying to encapsulate their properties, describe their braiding properties, which I'll talk about in just a sec. It's useful to think about them as sort of sitting on a line. It's useful to take a so-called blackboard projection where we think about them sitting on a line. That's just a subset of sort of anyon configurations that you can look at, for which it's sort of convenient to define these Berry phases that encapsulate the braiding. But in general, they can sort of sit anywhere in the 2-dimensional space.
Thanks.
Lukasz, may I ask a question regarding the previous slide about localized excitations?
Yes.
Can you explain again? Because suppose I have an excitation, which like an ionic excitation, which is not created by acting with a local observable.
Yes.
Then if I look at the, so D here is what exactly?
D is some topologically trivial disk-like region away from the excitations.
Oh, it's topologically trivial. Okay.
Yes. Yeah. That's right. So if I took D to be a ring about the excitation, obviously I could detect the topological charge.
All right. So localized means something which is indistinguishable from the ground state
on local patches.
In topologically trivial regions.
Topological trivial local patches. Okay.
Yeah. Okay. Thanks.
Yep.
Now here, I also have a question. For example, in a D class, when you put pi flux, Dirac fluxes, then they are also topological phases. You can braid them and you get different, non-trivial braiding rules. Yet is just a free fermion phase.
That's right. That's right. But that's right. And sort of that's an important point. I'll hopefully sort of get back to it when I talk about symmetry protected phases. But although that's not exactly a symmetry protected phase, but the important point here is that these are really excitations of a fixed Hamiltonian. When you're inserting a pi flux in a free fermion Hamiltonian, you're really changing the Hamiltonian. So those are more like defect excitations. But you're absolutely right. I mean, defect excitations are a more sort of generalized idea of sort of probing so-called symmetry protected topological order and various.
Okay, good point. Thank you.
Questions? Okay, so right, so so there's this spectrum of anyons. I've only really I haven't really even formally defined it, but to the extent that I've defined it as a set. But really, this set, let's say in 2 dimensions, actually has quite a bit more structure in there. It turns out that it has the structure of a unitary modular tensor category. So these anyons are isomorphism classes of objects in a unitary modular tensor category. You can braid them. There's braiding phases. There's exchange phases. There's this concept of fusion. There's sort of a lot of extra structure there, which is actually quite a rigid structure. And that whole structure, that unitary modular tensor category, you can think of as being an invariant of a phase. So this is the case for bosons. For fermions, there's something analogous. It's not quite modular because there's a localized fermion excitations, which has sort of trivial braiding with everything. But the point is that this is some kind of algebraic structure, unitary modular tensor category, which allows you to at least partially characterize phases of matter in 2 dimensions. Okay, the ones with intrinsic topological order. This works in higher dimensions as well. You can have, this definition of topological excitations in principle works in higher dimensions, but it turns out that the story in higher dimensions is a lot more complicated. So even in 3 dimensions, you know, you can have, well, you can already have line-like excitations, line-like anyons, but even sort of more than that, you can have excitations of limited mobility. So excitations which cannot be moved around sort of at will. They can only move along certain directions in these lattice spaces. So I think, so I'm not going to talk about that at all. These are still called fractons, but I just wanted to sort of mention that, you know, the situation in 3 dimensions is higher, is a lot more complicated. This is sort of an current area of active research, and I don't think sort of the right framework has been developed for sort of completely understood for thinking, for understanding fractons and things like this. So I'll mostly focus on 2 dimensions just because, at least in the context of intrinsic topological orders, just because it's the easiest thing to deal with. Okay. Let's see. So another important concept is the idea of symmetry. You know, so I mean, symmetry has been important in understanding phases for a long time. So far, what I've discussed, this idea of anyons, didn't rely on symmetry in any essential way. There was, you know, it's just the concept of excitations and which ones can be created locally and which ones can't. But there's sort of this additional ingredient of symmetry, additional extra structure. So, you know, on top of this tensor product Hilbert space and local Hamiltonian, you can have a symmetry, which in the simplest case, you can think of as just acting on site. Okay, so there's some, just for the simplest case, imagine some finite discrete symmetry group G, which acts as, you know, in a unitary way as a tensor product action over sites. Okay, so the simplest idea would be something like an Ising spin flip symmetry, which like flips all the spins. Okay, so you know, so what you can do when you have that kind of symmetry is you can consider Hamiltonians which are invariant under that symmetry, Hamiltonians which commute with the symmetry. And actually, just for simplicity, you know, here I said that the Hamiltonian should commute with the symmetry. Let me assume that all the terms in the Hamiltonian commute with the symmetry. It's slightly stronger, but that's sort of that's what I want to think about. So that's just, you know, that's a physically very natural idea to consider. It turns out that a lot of Hamiltonians do sort of naturally have a global symmetry like this, and this idea of symmetry, this idea of looking at Hamiltonians which are restricted to be invariant under the symmetry, commute with the symmetry, leads to a lot of you know, leads to an important idea for classifying phases of matter. And so this is the idea of spontaneous symmetry breaking. Okay, so again, this is an idea that sort of applies in the context of a general interacting many-body system. And I just want to emphasize that, you know, I mean, I'm sure, you know, many of you have seen this idea. I'm sort of giving a review, but again, we don't have a lot of ideas for treating sort of general interacting many-body quantum systems, and this is one of them, and it's an important one. So, you know, the idea. Was there a question? No. So the idea is that, you know, as you vary, I mean, so originally, I think this is the easiest way to understand this is when you look at phases at finite temperature and you vary temperature, but you can sort of just as well imagine varying, you know, staying at 0 temperature and varying some parameter in a Hamiltonian. So think about this as a quantum phase transition. But, you know, the idea is that as you vary some parameter in your Hamiltonian, the ground state of your, you know, the degrees of freedom in your system spontaneously order. Okay, so this can be formalized in terms of something called the local order parameter, which in the spontaneous symmetry breaking phase acquires off-diagonal long-range order. Okay, so you know, here on the left, let's say you have a paramagnet where there's not a lot of spin correlations between different values of the spin, but on the right you have long-range, off-diagonal long-range correlations, which means that the spin degree of freedom is correlated over very long distance scales. Okay, so a ferromagnet, you know, all the spins, in it is sort of the simplest caricature, all the spins could be up, all the spins could be down, sort of 2 possible ground states. And in either of those cases, the spin is correlated over long distance. If it's up here, you know, if it points up here, you know that it's going to point up sort of everywhere in space. So that this is encoded in this so-called idea of off-diagonal long-range order in terms of a local order parameter. But the reason that this is called spontaneous symmetry breaking is that sort of despite the fact that on the right side of this figure, the picture looks more orderly on the left, it turns out that on the right side of this figure, the system, the ground state, has less symmetry than on the left side, because for instance, here in a ferromagnet, there's a preferred direction for the spins to point. So the continuous rotation group symmetry, spin rotation symmetry, does not leave the ground state invariant. This is only invariant under spin rotations which preserve this particular axis, whereas here it's sort of there is no preferred direction. So the system really, it's kind of hard to draw. The system is really kind of a superposition of all these all these kinds of disordered configurations. But really, because there's no preferred direction on the left side here, the system has more symmetry here. This is the full spin rotation symmetry here, but here it has less symmetry. Okay, so this idea of spontaneous symmetry breaking, sort of classifying phases by the degree of symmetry that they break, was one of the original ideas of classifying phases of matter, and it just gives an invariant that you can assign to phases. How much symmetry, how much of the global symmetry did they break, and that's a way of classifying phases. So just to sort of have a caricature of the things that I've mentioned so far. So basically I've mentioned sort of two important techniques so far. I've mentioned this idea of intrinsic topological order, and for Hamiltonians which have symmetry, this idea of spontaneous symmetry breaking. Now what I want to do is I want to ignore both of these. Okay, so in other words, I want to see if anything is possible if I do not have intrinsic topological order and I do not have spontaneous symmetry breaking. Okay, so one of the motivations for this is, look, general many-body interacting problems are hard. Let's not try to solve sort of the most general problem, which can have all sorts of exotic phenomena like these anions appearing, or like symmetries which are broken spontaneously. Let's sort of think small at first, baby steps, and try to understand phases of matter systems where you don't have either of those possibilities. Okay, let's if we restrict ourselves to thinking about sort of a limited set of more limited set of systems, then maybe we can make more progress. Okay, so this caricature is supposed to describe sort of what we're going to be focusing on. So among so these various ovals represent gapped phases of matter, and there's one preferred phase, which is, okay, so far I'm thinking about no symmetry. So the one preferred phase is that of short-range entangled phases, or short-range entangled states. So this is the phase which has as one of its member Hamiltonians just the trivial decoupled Hamiltonian, which you can think of as a sum of projectors onto sort of particular states in this on each site of this many-body Hilbert space. So in other words, the ground state of one of these phases is just a trivial tensor product state, sort of as boring and as simple a state as you can possibly think of. So that sort of obviously can be made into the ground state of a gapped Hamiltonian, simply just individual projectors onto that state. And then there are other states, phases which might have anions, and then there's other phases which are not connected to a product state but don't have anions, which I don't want to talk about too much. These are so-called invertible phases. But my point is really that I want to focus on these short-range entangled phases for now. Okay, so these are basically states which are not very far away from the trivial tensor product state. They're sort of continuously connected to a trivial tensor product state. Now you might say, that's completely boring. Why would I want to do that? Sort of by definition, almost there's nothing here. This is the equivalence class of boring states. Why would I care? However, sort of the nice thing that was noticed, maybe 10 years ago or so, is that, or formalized 10 years ago, it was actually noticed by Haldane a lot earlier, is that if you include symmetry, so if you restrict yourself to looking at Hamiltonians which commute with symmetry, which have a certain external symmetry, Then there's actually something interesting that happens even in this sort of boring world of short-range entangled phases. Okay, so no anyons here. Morally speaking, these are all in the same phase without symmetry. But if you include symmetry, if you restrict to only Hamiltonians that commute with a certain symmetry, it turns out that you can have sort of non-trivial phases. You can have different non-trivial phases. And these are so-called symmetry protected topological, or SPT phases. So I want to emphasize that these phases not only sort of are short-range entangled in the sense that they have no intrinsic topological order, no anyons, but they also don't spontaneously break the symmetry. Okay, so it's not like these various phases are distinguished by different amounts of symmetry breaking. This idea of Landau-Ginsburg-Wilson that I described. These different SPT phases, sort of what the new and exciting thing was that you could have these different SPT phases, these sort of actual different phases, which were not distinguished on the basis of symmetry breaking and order parameters, and were not distinguished on the basis of intrinsic topological order, on the basis of anyons. So this was really something new. This was these phases should look boring by all accounts, but nevertheless there are interesting phases here. Okay, and so those are the kinds of phases that I want to sort of discuss for the rest of the talk, which I guess isn't for too long now. So, I guess I'm not finished, but I was kind of late. Is it okay if I take 10 more minutes, or do we need to end right now?
No, sure. We can have another 10 minutes because it's
okay.
Yeah.
Okay. Yeah, great. Thanks. Right. So these symmetry protected topological phases, these SPT phases, have been sort of an intense area of research interest in the last 10 years or so. There are sort of various different ways of understanding why you can have these these symmetry protected phases which don't differ on the basis of symmetry breaking and don't differ on the basis of sort of anyons because they don't have any. So there's sort of various ways to extract quantized invariants which differentiate between these different symmetry protected topological phases. So let me describe a few of them, and then let me talk about this sort of quantum information theoretic approach, which I think is really nice for probing them. So originally, sort of the original way of understanding these SPT phases is by saying, well, look, you have a global symmetry here. This is a system with a global symmetry. One thing that we know we can always do with a global symmetry is gauge it. So this means various things to various people. It's kind of a fraught word, so you have gauge. But at the level of lattice systems, this actually means something very specific. There's a very well-defined prescription of taking any system with a global unitary symmetry acting on the lattice and coupling to a background gauge field of that symmetry. So this is really sort of an algorithm, a prescription for taking a Hamiltonian with a global symmetry and constructing another Hamiltonian, which has no global symmetry, but which has a gauge field corresponding to that symmetry. And whereas the original Hamiltonian is sort of boring and short range entangled in the sense that its ground state is continuously connected to a product state, the gauge theory Hamiltonian has intrinsic topological order. And in fact, this is true. This is a way of understanding sort of the simplest example of intrinsic topological order, which is that of the toric code. The toric code is nothing but starting with, it could sort of be understood by starting with a boring Hamiltonian with a Z2 global symmetry and just a simple tensor product ground state, and coupling it to a background Z2 gauge field. That's what gives you the toric code. And what was found was that in the case of the Z2 symmetry that I'm talking about right now, we'll just stick with Z2 symmetry. In addition to sort of this boring, phase with Z2 global symmetry, which is just a trivial tensor product state, there exists a non-trivial SPT phase. And the way that this non-trivial SPT phase is characterized is that when you carry out this coupling prescription to a background gauge field and you look at the resulting resulting model, it gives you an intrinsic topological order that's different from the Tor code topological order. So, and this is just seen in the spectrum of anyons and their braiding excitations, as I mentioned previously. So it has a different unitary modular tensor category. Okay, so this is a very general idea, and it turns out to work for general symmetries that, you know, this coupling this prescription of coupling to a background gauge field gives you a theory with topological order, and the unitary modular tensor category associated to that to that theory. So in other words, the spectrum of anyons and their braiding is somehow a hallmark of the original SPT phase. Okay, so this is sort of a nice way of relating systems with symmetry to those with topological order by gauging. And so this is, you know, this is something that it really has tight connections to continuum topological quantum field theory. These ideas really come from like Diagraph and Witten ideas in topological quantum field theory. And there's sort of, you know, a lot of formal mathematical work done on sort of classifying these kinds of topological quantum field theories. So this is, you know, something that you know, Anton obviously has done a great deal of work on. People like Dan Fried, Mike Hopkins. There's an entire mathematical framework, in this case, invertible topological quantum field theory, which sort of captures the kinds of mathematical structures that are relevant for these kinds of models. I do want to emphasize, though, that you know, there's still kind of a gulf between this kind of topological quantum field theory approach, which really works in the continuum. So you know, it assigns invariance to, you know, non-trivial space-time manifolds and various structures on them, like, you know, symmetry bundles. And the lattice. Okay, so in certain cases we know how to make this work, and in sort of the simplest examples of SPT phases, we know how to sort of make this correspondence work. Anton's done a lot of very nice work on sort of extending that and really making it understandable in general. But I think there's still, you know, we think there's still some, you know, there's still a bit of a gulf between sort of this continuum picture and really applications to lattice. So in the remaining 5 minutes or so, I just want to mention something about this quantum information theoretic approach, which, you know, one of its virtues is that it's sort of more closely tied to the lattice. So it's a way of sort of really directly trying to understand these SPT phases on the lattice without sort of appeals to topological quantum field theory of the continuum or anything like that. Okay, so sort of I'll keep watching time. So the key idea here, the key idea for behind this sort of quantum information theoretic approach for understanding SPT phases is the idea of a finite depth quantum circuit of local unitaries. Okay, so the basic intuition is this. The basic intuition is that, remember, we're trying to understand this set of short range entangled states. So there's this sort of oval on the left side of the screen that I had a while earlier. And so the key point was that within this oval, there was a special state or a special Hamiltonian with an associated state, which was just a trivial tensor product ground state. The idea is that, you know, since any other state in that oval can be reached by continuously varying parameters in the Hamiltonian, that's sort of the definition of having a phase. You know, any state in this short range set of short range entangled states can be reached from this trivial tensor product state by continuously varying parameters. It turns out that implies, using this idea of adiabatic continuation, that there's some time ordered exponential of a sort of local pseudo Hamiltonian, which you can apply to the initial tensor product states to reach any desired short range entangled state. Okay, so there is a formalism which I don't have time to describe here, but the intuition is sort of this idea of just adiabatic continuation. You sort of slowly adiabatically make changes to your Hamiltonian, and as you do so, you can sort of get the new Hamiltonian, get the new ground state from the old ground state by applying a certain, you know, certain sort of local pseudo Hamiltonian. There's when the system is gapped, this pseudo Hamiltonian is indeed more or less local. There's a discrete version of this, which is this idea of a finite depth circuit of local unitaries. So the idea here is that, you know, your Hilbert space is, you know, a Hilbert space of qubits here. I've only drawn it in one dimension. And you can imagine feeding in a simple tensor product state initially, and then applying some finite depth circuit. So the finite depth circuit consists of finitely many layers, finitely even in the sort of limit of thermodynamic limit of large system size, applying finitely many layers, where in each layer you apply a set of unitary quantum gates that act on some finite number of qubits. So finite, there's some finite range of the interactions for this finite depth quantum circuit, and you apply unitary gates that act on disjoint sets of qubits. Okay, so this is kind of a discrete version of this time-ordered exponential of the local pseudo-Hamiltonian. So this is something that can sort of be used. Okay, I mean, there's obviously none of this is rigorous, and this is sort of it's just sort of this patchwork of ideas. But the idea is that we believe that any one of these SPT phases, so any one of these phases here, can be reached by starting with a simple symmetric tensor product state and applying one of these finite depth circuits to it. Okay, and somehow we want to understand the properties of the SPT phase that we make in terms of the properties of this finite depth circuit. Okay, so so for example, what we know, so just to give you some intuition, what we know is that we start with a fully symmetric state, it's sort of trivial tensor product state. We make another fully symmetric state, the ground state of our desired SPT Hamiltonian. And we know that if this SPT is non-trivial, it means that it's not possible to choose all these unitary gates to commute with the symmetry. If they all commuted with the symmetry, then we would not have, we would, let's say SPT1 is our boring SPT, we would not have reached a non-trivial SPT because somehow we would have stayed in the boring one. If all these unitary gates are commute with the symmetry, then somehow by applying all these gates, we're really staying in the same phase. So the sort of non-trivial SPT properties are encoded in the fact that this finite depth quantum circuit, even though it creates a symmetric state from a symmetric state, somehow its gates cannot all be symmetric, cannot all have this symmetry property. Okay, so then there's sort of a game that we can play, which is to try to classify SPT phases based on the properties of this circuit B. Here I call this the Entangler Circuit because it entangles the qubit in this sort of symmetric product state to make the SPT ground state. So one question that you can, for instance, ask is, well, I know that I can't choose all the gates in the circuit B, this Entangler Circuit, to be symmetric, but there's a natural question, can the circuit overall, just as an operator, be chosen to be symmetric? So this is, can it commute with all the symmetry generators? I mean, it prepares a symmetric state. It prepares one symmetric state by acting on another symmetric state. So, maybe the whole thing can be chosen to be symmetric. And this is actually a very interesting question to ask. So it turns out that for some SPT phases, the circuit can be chosen to be overall symmetric, and for some, there's an obstruction and cannot. And so, for instance, there's a famous phase called the so-called beyond cohomology phase, protected by time reversal symmetry in 3 dimensions, where it turns out that this entangler cannot be chosen to be symmetric. There's a fundamental obstruction to choosing it to be symmetric, and this is related to actually the existence of something called the non-trivial quantum cellular automaton, which is an operator that kind of looks like a finite depth circuit. It's sort of a so-called locality preserving operator, which nevertheless cannot be a finite depth circuit. So that's related. It's not sort of directly related, but it's partially related. The last thing I want to say is, if we do focus on phases which have a symmetric disentangler, so again, the gates of the circuit might not be symmetric, but the operator overall is symmetric, then it turns out that we can make sort of quite a bit of progress by, in classifying such phases, which include actually all the so-called famous in-group cohomology phases, by studying properties of this disentangler. And so the basic idea is that, if we have a symmetric disentangler, so this is acting on a system without boundary, So I should have said that before. So if we have a symmetric disentangler on a system without boundary, like we say with periodic boundary conditions, we can always truncate that disentangler to act on a system with boundary. So just act on the bulk of a system with boundary. So that's this jagged edge is supposed to denote the truncation of a finite depth circuit. And the fact that it's a disentangler means that it acts on this oval, which is a sort of, correlated SPT state, and disentangles the bulk of it. Okay, leaves the edges entangled, but disentangles the bulk of it. So if you have a disentangler, a truncated disentangler like that, then what you can do is you can conjugate the group action. This is just the act on-site symmetry action. You can conjugate it by this kind of disentangler, and it turns out that this has the property that it generates for you an effective boundary action of this symmetry. Okay, so this is a way of sort of formalizing a very simple idea, which is that if you're in an SPT phase with a symmetric ground state, the bulk is symmetric. The boundary might not be. The boundary might contain gapless excitations or do whatever. Then the global action of the symmetry can sort of be simulated by acting on the boundary. Okay, because the bulk is symmetric anyway. So even though you are acting with the global symmetry in the bulk, because the bulk is symmetric anyway, things can just be simulated by acting on the boundary. So there's this notion of effective boundary action of the symmetry, and so this effective boundary action of the symmetry can be used the properties of this effective boundary action can be used to classify SPT phases. So this was sort of most simply done in one dimension. In one dimension, this effective boundary action is just sort of acts near both the left and right endpoint. And it turns out there are some irremovable phases which prevent these individual left or right actions from satisfying the group law. And these irremovable vary phases define so-called group cohomology class. And this is sort of the situation that persists in a spin 1 Heisenberg antiferromagnet. So because I'm out of time, I don't want to sort of go on. There's more I could say about this in higher dimensions, but let me just sort of leave with the statement that this is just sort of the simplest way in which this effective boundary symmetry action can be used to classify phases. This one-dimensional idea. It turns out that this can be generalized to higher dimensions. So you can define this notion of effective boundary action in higher dimensions, and you can sort of usefully classify phases in higher dimensions by understanding the properties of this effective boundary action in higher dimensions. So this was done originally by Chetan Nayak and Dominic Elsa, but it turns out that there's sort of a very rich structure of these effective boundary actions. You can sort of try to understand the properties of these effective boundary actions as finite depth circuits acting in a lower dimension, and you can actually use this to give a way of classifying group cohomology SPT phases sort of in all possible dimensions. There's sort of an entire procedure. This is the kind of the first step in an entire procedure, entire hierarchy, which allows you to classify these incohomology SPT phases. One of the things that I personally worked on recently with Matt Hastings and Zhengwan Ha is in extending this idea of Elsa and Nayak to more general phases, these beyond cohomology SPT phases. And it turns out that there's some very deep connections between sort of the topological TQFT invariants that come up in classifying these beyond cohomology SPT phases and the properties of the various circuits that appear in this kind of lattice-based quantum information theoretic Elsa-Nayak description. So it turns out there's some very deep connections between the quantum cellular automata on the one hand and ideas from topological quantum field theory and sort of very, very much continuum-based ideas. And I think this is sort of a rich area for further investigation. Okay, but since I'm out of time, let me end here and perhaps pause to take questions.
Thank you, Lucas. Thanks for a very nice review. And we can take a few questions.
Thank you. I have a general comment, not a question, but it's addressed to the whole audience. It's exactly about this slide where these U's, perhaps one will see them as automorphisms on the algebra. And if we think about our bulk boundary picture, which is put in this extension of the bulk algebra, then this one seems to fit somehow, that you have a symmetry in the bulk. It's an endomorphism, and if you filter it out through this exact sequence, it should boil down to a projective representation, possible projective representation on the boundary algebra. Something that it's worth looking at, I'll say.
Is this something you can generalize to higher dimensions, like when you have, I don't know, one-dimensional boundary? Because there you don't expect a projective representation. You expect one of these sort of H3 invariants.
Emil, I think your question is going to belong to this discussion section we're going to have after this. It's really, yeah, we can discuss that.
Okay.
And there are actually generalizations to higher dimensions, which LUKASZ mentioned, so we can discuss that. But yeah, the point is this is a very nice paper of Nayak and Else, which LUKASZ has mentioned.
Yeah.
And it explained in principle the strategy to extend it to higher dimensions. So yeah, we can discuss that, but there's some technical issues, again, mentioned by LUKASZ, because starting from dimension 3, you need to make some assumptions which in general don't hold, so that you don't get the complete picture.
Exactly.
So that's related to the existence of this non-trivial cellular automata in dimension 3.
Exactly. Yeah.
So that's still work in progress. But in dimension 1 and 2, by the way, recently there was a rigorous work on that too by Ogata and also by my student Nikita Sepenko.
Yeah, that's right. I think I heard about some of this work. Yeah, that's right.
In dimension 1 and 2, it can be done completely rigorously.
Right.
Dimension 3, it's principle. It's clear. I'm going to talk about it actually, how in principle to approach this rigorously. But there is this reducible physical or whatever technical issue about cellular automata.
Yeah. So you know, Matt Hastings and Mike Friedman did prove recently that there are sort of no non-trivial quantum cellular automata in dimension 2.
Yeah.
So so that can be useful in sort of class. So there, as soon as you have a symmetric disentangler in dimension 3, then you have a boundary action in dimension 2, and then you can apply those results, I think. So
those results, by the way, should be very important for also showing that these indices, this group, elements of H2 and H3 actually into dimensions, for example, are complete invariant when we determine the SPT phase, which has been done. But anyway, we can just leave it to the discussion section, because any concrete questions to LUKASZ?
Yeah, well, my concrete question is, if these U hats in these slides, are they exact operators, or is this an equality or an approximate equality?
Okay, that's a good question. So, you know, in that depends on the Hamiltonian. If you have this is a property of a phase. So if you happen to work with like a commuting projector Hamiltonian for this phase, one of these idealized models, then this would be an exact equality, and this U hat would act on some finite number of sides. But for general Hamiltonian in this phase, it's an approximation. So this UL is supported on some finite number of correlation lengths, and sort of the quality of approximation is like e to the minus size of the support divided by correlation length. It's approximate. Absolutely.
But if you could do this on the half line, then it would be exact. Because this is only limited by the distance between these 2 points.
Yeah. But then you would have to have formally the support of one of these operators would still be infinite, even though it's sort of not really touching very strongly the sites that are.
The boundary, you're saying that if you act on half of a line with a symmetry, that's the same as just acting on something local on the boundary of this half line that is at the point.
Yeah, but it's not strictly local.
Not strictly local.
They have the
exponential tails. Yeah.
But there's no exponential. Like if you're on half line, there's no distance scale, because the distance scales are because you have 2 points on the line, right?
Well, there's a lattice length. I mean.
No, but I think
there's still a correlation line.
You can make it exact. You can make this exact. if you're on a half line. Because
You can.
yeah.
It's just that you will have to have your operator be supported on sort of infinitely many sites to make it exact,
Yes.
which you might be okay with.
yeah, it's spread out a little bit, but
Oh yeah, sure, yeah, absolutely.
yeah, if U is strictly local, like, then it's only approximate. But if you allow U like to have tails,
Exactly.
then it can be.
Now, can I ask here, what will take in this H2G U1 to change the group U1 to something else? Why not?
Well, okay, so let me say this. I mean, okay, this is the answer that arises for classifying 1D phases, SPT phases, but the group H2G with some other coefficients does appear in other contexts, like, for example, classifying symmetry-enriched phases of symmetry-enriched topological phases. So basically, let's say in 2 dimensions, phases which have both intrinsic topological order and a global symmetry action. So there, you know, if you want to understand sort of the various patterns of symmetry-enriched topological phases, then there's a group that appears in the classification, which is like H2 of G with coefficients, you know, let's say the anyons are abelian, the group of the anyons. And so that's sort of the charges that can be, you know, that's not like the, no, this is like the projective representations carried by the endpoints. There, it's like the projective representations carried by the anyons. And because anyons must obey certain fusion rules, that restricts these coefficients, and that's what gives you the coefficients.
Let's see. There's some other.
Chris has his hand up.
Oh, yeah.
It's just a naive question, though.
So
Sorry. It's a very maybe stupid question, but you talked about how in the sort of field theoretic viewpoint, when you have an SPT phase, you can couple it to an external gauge field, and then you get a modular tensor category. So anyons appear. I guess when you're looking at this information theoretic approach with the finite depth unitary circuit, you probably can't do this, right? Because, or can you? Because I would think that because you're doing local operations, you would not be able to somehow bring in something which has intrinsic topological order. But
right. Yeah, I mean, yeah. So I would say this. You know, there's this. Yeah. So you know, when we couple an SPT phase to you know, one of these gauge fields, these symmetry gauge fields, what we're really doing is we're taking the symmetry defects, which are not localized excitations, but they're sort of, you know, excitations where you change the Hamiltonians and put in a symmetry flux, and making them dynamical in order to then just apply our sort of standard formalism about anyons and braiding anyons and things like that. But you know, really what we're doing is sort of braiding and acting on and playing around with symmetry defects in our system. And so what this circuit formalism does is it plays around with sort of the same set of defects, but it just doesn't sort of do this extra step of, you know, making them sort of formally dynamical excitations. But I don't think that's sort of a sort of crucially important step. That's just sort of a nice conceptual thing. But yeah, so the circuits do really kind of play around with these defects. You know, these various properties of these circuits, like, you know, this Berry phase here, you know, that appears here in this boundary symmetry action in the space-time formalism. You can really think of this as coming from the fusion of 2 defects at this 0+1 dimensional boundary, 2 symmetry defects being fused at this. Well, they're being fused at the bulk, but they're sort of going into the boundary. So and in higher dimensions, this is even slightly more vivid. So I would say that the circuit formalism does manipulate these kinds of symmetry defects, but doesn't formally couple them to background gauge fields.
Right. Okay. All right. Thanks.
Okay, let's see. So I guess let's thank LUKASZ again. And do we need a break for this?